Hello, my name is Chris Comire. I'm with Advanced Electrical Motor Control, and today we're here taking a look at a 3,000 amp Pringle. What's unusual about this switch is that it's so old. According to the paperwork, the switch itself was manufactured in 1969, which makes the switch about 53 years old. This came out of our inventory. Typically a switch like this we would save, really not for reapplication, for reuse, but to retain the technical data, the dimensional data, for a later refitment, where we would take a newer device, a switching element, say an insulator or molded case breaker, maybe even a switch, something more modern, and replace it in the hole that this is now existing. The customer happens to have a switch exactly like this in service, but they won't have a large window of time to troubleshoot it, so they're looking for a replacement. Something to point out here is the original baseboard, how thick it is, and part of that is for the strength of this board, because we're used to more of a fiberglass resin type of board today, which would be half the thickness. This is manufactured out of some type of paper or wood-based fiber phenolic. They used a what we would call a canvas phenolic type material for the crossbar, to give it enough strength to push all this energy into the contacts. The contacts themselves, the moving element of the contacts, are not heavily grease lubricated like we see today. It appears that they lubricate it with a coat of carbon, almost like a dry lubricant technique, which I thought was very, very interesting. This polynoid is really a linear motor. So where we're used to seeing the heavy solenoids that operate at a high amp, usually a DC voltage, that had a very limited stroke due to the magnetic field, for that short coil, this has a progressive field. It's just phase after phase after phase, acts just like a motor, but instead of rotating, it runs down a straight shaft. To do a close operation, this thing has an interlock, an electrical interlock. And so when you press this button, it should cut off all the electrical operation to the device. And then to close it, you'd probably want to be as swift as possible closing a device like this. This is actually a slow close device. A modern Pringle switch would have a stored energy mechanism that would really charge the springs, and you'd get to a point of release and the springs would take over and close the device. So you couldn't close it as slow as the operator. This device, like I said, will open and close as slow as the operator. So we can open it, we can close it, but probably you either got to be really quick or you're doing it for maintenance purposes only, All right, but the way this breaker or switch was intended to operate was electrically. So we're going to operate electric, close operation, nice and snappy. Open operation, equally quick. Let's close it one more time. Quick close operation. Now the overcurrent protection on the switch would have been provided by the fuses, which would be the short circuit and overload protection. And this device has an early form of a ground fault protection. So there would have been a coil in the gear, a current transformer that would have monitored all phases, all current carrying conductors, A, B, C, and neutral. And when it produced a certain voltage, it would put certain amps, it would transfer that amps back to this device. And we tested this device, and at 7.5 amps it picks up. So a 1200 to 5 amp current transformer, somewhere in that 1600 amp range, it would have tripped this device. A low energy trip, which is something we didn't see in a lot of early devices. So this is kind of the early attempt at it.